So we're still talking about RC circuits. But I want to focus not just on the transient nature of the circuit. I really want to focus on stuff that's in the homework. Dealing with circuits at time equals 0 versus the steady state condition. So let's start with two basic circuits. Not an RC circuit, two basic circuits. Both of them ideal circuits based on what we've talked about so far in class. And I need a way to differentiate voltage for us. So if putting that there is too disconcerting, how about I just do VB for the battery? Is that okay? Later in the year, we're going to dispense with this once we get into second semester, and we will replace it with a script E, which represents EMF, because we'll be talking about EMF second semester, and we'll have a symbol that we'll use more prominently for our battery. But this semester, plus what's on the semester exam, I want to stick with V for battery. So in both of these batteries, I want to remind you that when you connect your device to the battery, there are things about the device that are constant, that aren't based on the battery. For example, the value of the resistance has nothing to do with the battery. It has to do with what you've connected to your battery. The thing that is related to the battery and the resistance is the current. The current depends on these things. For a capacitor, the capacitance is based on the device. But the charge on the capacitor will be based on the battery and the capacitance. These are things we talk about. These are the dependent relationships. Now, in our activity and in our discussion prior to it, we talked about what happens when we have a circuit that has a transient nature to it. There. Same resistor, same capacitor, same battery. Closing the switch represents T equals 0. On an uncharged capacitor, when we close the switch, we generate a current. But that current changes over time. So I want to come back and focus on these things for a minute, because they represent two cases in which there's no transients, right? They were steady state conditions because those circuits didn't change from the moment they were connected to the moment they were disconnected. They stayed the same. But in this circuit, we have a transient condition. And for the capacitor, the only thing we solved for was the transient function for the capacitor. Right? And you should have a relationship for that. That transient function came out to be Q times 1 minus e to the minus t over RC, where Q represented the maximum charge on the capacitor. Q came from this being equal to VB times C. That's why I replaced it with capital Q, representing the charge that would be on the capacitor in its steady state, if there was no resistor in the way, the full charge on the capacitor. Now, we examined this and talked about the fact that at time equals 0, there's no charge on the capacitor. That's Q when T equals 0 equals 0. This is the initial condition, switch closed, right, T equals 0, right when we close the switch. And steady state, Q for T equals infinity equals Q, capital Q, represented by VB times C. That okay? Well, we derived a voltage function by dividing both sides of the charge function by C. When I do that, I get the voltage over the capacitor. That's got to be equal to Apparently the voltage over the battery, I just took this, divided both sides by C, that gave me the voltage over the battery. The voltage I would expect if there was no resistor in the circuit. And then I have my asymptotic model, the growth portion of the voltage. This is what we just showed. And this is what you showed in the lab. You never measured charge, you measured voltage and got the expected result. Now, I then asked you to take the original charge function and find dq dt, because this is the current in the circuit. Sound familiar, right? I hope. It was kind of loud, but that's okay. It's good to have a loud sneeze. It means you move some stuff around. If you don't remember what this came out to, it was Q over RC e to the minus T over RC. And I'm trying to be careful here because I'm trying to make sure you see what we did to get each piece. Q divided by C, voltage of the battery. But VB over R is the current as if there was no capacitor in the circuit at all. So capital I. And I'm putting a capital I here because it represents the current as if there was no capacitor in the circuit. I've said that like twice, right? Now, this function starts at a maximum and then decreases over time. You measured that. You saw that that was what happened in your circuit. The current decreases over time, which is why the voltage across the resistor has to equal I times the size of the resistance. Right? Ohm's law. If I replace I with my function, I replace this, I'll get IR e to the minus T over RC. Okay, I times R. That's Ohm's law again. This is the maximum current times the resistance, has to be the voltage across the battery. Now, this is what we just saw, these two things. We plotted them side by side, and we saw that exactly as it happened in real time. The voltage across the resistor was dropping, while the voltage across the capacitor was rising. And this total always equaled the voltage across the battery. And not a surprise, if I add those two things up, I get VB times 1 minus e to the negative T over RC plus VB e to the minus T over RC. If I look just at that, adding up all the voltages and looking for the total voltage, do you see that you just get VB, the voltage across the battery? This transient circuit has a constant net change in potential. It's just that the potential is going from one thing to the other. Now, I'm trying to throw all this out there because what I want you to see next, or what I want you to understand, is more complicated. And you have to have it fast. So, although this is a mess, if I were to clean it up, all RC circuits have some portion of the circuit that's in transients. I'm saying that because our circuits are going to get more complex. So voltage of the battery, resistance, capacitor. I'm going to try and put this all in one place. So Q, no, let's just do it this way. Capacitor. Q equals Q to the 1 minus e to the minus t over RC. V over the capacitor equals V battery times 1 minus e to the minus t over RC. Resistor. V over the resistor equals V of the battery, e to the minus t over RC. And current through the resistor, I to the e minus t over RC. And in all cases, Q is VB times C, and I is VB over R. That's everything in one place. Now, this part's tough because you aren't really paying attention. I can tell. You're just hurrying in your writing, and although I've repeated myself, this part you're going to ask questions on and not understand. At t equals 0, the capacitor has 0 resistance. That should be clear. It's probably not. So prove it to yourself. Look closely. At t equals 0, there is no voltage across the capacitor. Therefore, it's as if it has 0 resistance. An uncharged capacitor appears as no resistance to the circuit it's in. I've said it 4 different ways. Pick one that makes sense to you. An uncharged capacitor appears as 0 resistance. Yeah?
Does that have to do with the spike that we saw in our graphs?
No, the spike is something else completely. And I'll discuss the spike in a minute. That's a example of a real circuit versus an ideal circuit, something else that's happening. We're still dealing with the idealized circuit here. So when you first close the switch, it's as if the capacitor has 0 resistance. It's like it's not there, it's just a wire. Now, contrast that with the steady state. In the steady state, the capacitor has infinite resistance. In the steady state, the capacitor has infinite resistance. When it is fully charged, the capacitor acts as though it has infinite resistance. All right, so the look on the faces is, so care about that, Mr. Shelton. Okay. Yeah. For those of you who maybe have been asleep for the last few minutes, this would be a good time to wake up. This is what you're going to be expected to do. Not only an RC circuit with the transients, but notice that in this circuit, you've got something else going on. So I'm going to ask you a question. I don't know if you can answer it. But if I close the switch at t equals 0, what is the current across the 6 ohm resistor?
0.
Nope. That's why you should pay closer attention. Look, guys, try it. Take what I just gave you for notes, apply it, and find the answer. So just try it. Take a minute. Talk to the person next to you. Don't jump at an answer. At t equals 0. It's as if the capacitor has 0 resistance. So at t equals 0, it's as if this is my circuit. If I draw a loop through my circuit, now you're asking what would be the current through the 6 ohm resistor? It would be 0. Because there will be no potential difference from here to here. Path of least resistance. There'll be no current. If you try to figure out right now what is the equivalent resistance here, it's 0. That means, of course, that there will be 6 amps through the 3 ohm resistor. Now, that being said, you understand exactly what the next question is going to be, right? What is the steady state condition? So at t goes to infinity, what is the current through the 6 ohm resistor? I think that one's a little easier, isn't it? Now that we're understanding what we have to do here. In the steady state condition, the capacitor becomes fully charged. And when it becomes fully charged, the resistance across the capacitor is infinite, which means in the steady state condition, that's my circuit. So, 2 amps. Steady state versus initial state. Now, I'd love to say we're done, but of course, the very next question I would want to ask is how much energy is charged in the capacitor, or how much charge is across the capacitor? To answer that, you need to figure out what voltage is across the capacitor. Do you know how to do that? You should, because you can figure out the voltage across this resistor. Hand down. I'll answer in a minute. You can figure out the voltage across that resistor. You know how the circuit operates. It's just 2 resistors in series, so you can figure out the voltage across that resistor. Okay, Jeremy.
Why wouldn't the capacitor discharge like automatically? Because it's in a closed loop, so wouldn't it be able to discharge without the source?
Well, the question you're asking isn't inappropriate, but you're just a little ahead of yourself. Why would it discharge when there's an applied potential difference across its terminals? Right? Look, there's 2 amps passing through this resistor when we're in a steady state condition. Correct? We just did this.
Yes.
Which means there's 6 volts across that resistor.
Right.
Which means there's 12 volts across this resistor. But that also means that the terminals of the capacitor are being maintained at 12 volts. So the capacitor can't discharge, can't push current up. It can't push current against the potential difference that's being applied to it. So it will fully charge and stay that way as long as this 18 volts stays connected to the circuit. Which, by the way, means that there's 24 microcoulombs of charge stored on the capacitor. That's the answer to the question I asked. Now, at the same time, and this is important, when we open this switch, the story's not over. When we open this switch, the capacitor is fully charged and has a means to discharge that energy through the 6 ohm resistor, which means you suddenly have a new discharge cycle using the 6 ohm resistance as the resistance for the circuit. The whole system changes to be this. 12 volts. Now, there's plenty of ways to express this problem, but this is what the AP exam is going to be like. This is what the RC circuits are like on the exam. You're going to get these, multiple choice and probably FRQ. The transient circuit for just the R and C is one thing, but to be able to deal with it in a more complicated circuit, that's another. Now, this probably gives you some information that will assist you with your homework. But one of the circuits in your homework, I believe, look like this.
Oh, yeah.
And then there was a switch here, right?
Yep.
Now, this is a more complicated problem than it looks like. It's pretty easy to deal with the RC sides of each of the circuit. You can figure out the voltage across both of these in the long term. Really easy. Because in the long term, that'll be 0, and that'll be 0. And this will be whatever the battery is, and this will be whatever the battery is. But when you flip this switch, you make a complete pathway through the battery that cuts out the capacitors completely. Right? Current can travel this pathway when that switch is closed. All right. We'll talk about homework, I guess, on Monday.